Okay, so we're going to be looking at what's called the Rayleigh-Ritz method. Basically, it's a convenient procedure for finding solutions by using potential energy. So basically how you do this is you start off by finding an expression for the deflection curve, and usually this is given like it'd be, for a simply supported beam, it'd be something like V, which is deflection, is equal to AXL minus X, which is just at a certain point. Like say you got a point load at a point like this, then this is not a great drawing, but this would be the equation, and usually this equation's given, so you don't really need to worry about that. Second, you need to find the potential energy, which is this pi symbol in terms of A, and this is the equation that you use right here, where U is the potential energy, which is just always this equation, and the work is just the point load times deflection, this equation right here. And then from there you take the derivative of this with respect to A, like the derivative of this with respect to A, which will give you an equation, and then you can solve for A, which is your constant, which was found here in this step. And then basically all you have to do is plug that constant back into step one, and then from there you can find your deflection at a certain point, which was specified in step one. I don't know if that made sense, but we'll do an example here and I'll see if I can explain it a little better. So this question is just a simply supported beam like this, and it's got a point load P at a distance of Z from this end here. We can call that A, I guess, and this is B. That. So the question is to find the deflection at this point P right here, and the deflection curve, which is what I explained in step one, was given. Like I said, here usually it's given. So here the deflection curve equation is V is AX times L minus X. So the solution, step one, we know the equation for deflection curve is V times AX times L minus X. Then we need to take the derivative of that so we can get it in the form of V double prime. So we'll take the first derivative, which is equal to A times L minus 2 times AX, and we'll take the derivative again so we can get it in that equation, and this is just equal to negative 2A because it's the derivative with respect to X, so this just becomes negative 2A. Then from here, step two, we're going to find the minimum potential energy, which is U minus W. So we saw in those steps that this is just equal to E over 2, EI over 2, from 0 to L, times V double prime squared, and it's always going to be this equation here, times dx minus P times V, because work is equal to P times V. And then now we're just going to plug this into here, and we know V is equal to this, so this just becomes EI over 2 times negative 2A squared minus P, and because this force is at a distance Z, we'll make this equation right here in terms of Z, so this becomes minus P times, instead of AX it'll be AZ times L minus Z, and this is fairly easy to solve. This equals to 2A squared EI times L minus P times AZ plus PAZ squared. And this is equal to pi, which is the minimum potential energy right here. And then third, we take the derivative of this with respect to A. So we can solve for A, which is the constant, and set it equal to 0. So basically D, that becomes, and then we plug this back into here. So that becomes, just plugging this in actually first, minus PAZ plus PAZ squared. And that's equal to 4 AEI L minus PZL PZ squared. And that's equal to 0. Then from here you can just solve for A. So A becomes P times Z L minus Z over 4EIL. Okay, so we have A here. And now step 4. What we're going to do now is find the equation, or sorry, the deflection at this point right here. So all we have to do now is plug A back into here, and it's in terms of Z, right, because it's at a distance Z from this point here, and that's where P is acting. So we'll make this in terms of Z instead of X, and then we'll plug the value of A that we just found back into that. So V is AX times L minus X, sorry. And that's at point Z, so this becomes A times Z, L minus Z. And then we know A, we solved it in part 3 there. So this becomes P, this is A here, PZ Z over 4EIL times Z, because this is in terms of Z, times L minus Z. So this ends up equaling PZ squared over 6EI times L. And this is equal to the deflection at point Z right here. We're calling this Z the point load, the distance Z from point A. So the deflection at point Z would be equal to this. So basically that's all it is. A lot of the problems are pretty similar, so kind of just need to follow those steps and you should be okay. Thanks.